So earlier we were calculating the delta H of chemical reactions using the idea of the sum of bond enthalpies of bonds broken minus sum of bond enthalpies of bonds formed. That's what we had done earlier. So finding delta H via bond enthalpies. Now there are two ways to find delta H using bond enthalpies. So one of them was just simply, like I mentioned just now, and I'm putting that formula that we saw last for you to see. That was this idea that delta H of a reaction could be found by the sum of all the bonds broken minus the sum of all the bonds formed. That's one way of finding delta H of a reaction using bond enthalpies. The second way, the way I prefer more, is using Hess cycle and bond enthalpies. So basically, if you have, for example, like if you remember, the first example we did was HCl, right? So so if you wanted to find the bond the delta H of the reaction between H2 and Cl2 making 2HCl, one way is to find our bonds broken minus all the bonds formed. That's one way. The other way that I prefer, and that's sometimes given in MCQs also, is basically use this as boxes A and B. So the reaction given to you becomes boxes A and B in a Hess cycle. And box C becomes what we call gaseous atoms from everything. What that means is, if you break H2, what are the gaseous atoms you're going to make? You're going to make 2H gaseous atoms. If you break Cl2, you're going to make 2Cl gaseous atoms. And 2H gaseous atoms and 2Cl gaseous atoms may, if 1H and 1Cl react, they make 1HCl. If 2H and 2Cl react, they make 2HCl. So you might say, okay, so bonds breaking minus bonds forming. But I would prefer the other way, which is what we do is we break everybody's bond. So now, for example, if this is not a chemical reaction and you had to break the bonds of H2, what would that be? If I say break the bonds of H2, you would make 2H gaseous atoms. That would be this blue arrow. Then if I say, okay, break all the chlorine bonds, you would make it into 2Cl atoms. That's this one right here. And then if I said, okay, now break the HCl bonds. So if you break one HCl bond, you get one H gas and one Cl gaseous atom. That is if you break HCl's bond. So if you break two HCl's bond, you're going to get two H atoms and two Cl atoms. So now, basically what happens is this blue arrow, and by the way, all these three arrows are bond breaking. They're all positive. All these three arrows are going to be positive. All of three are going to be positive. The blue one will be the bond energy of HH. Let's say I tell you that the bond energy of HH is 436. If I tell you the bond energy of chlorine, ClCl is 242. And the bond energy of HCl, which is 431. So this one is 431 times 2, because 2 bonds have been broken. So now what I've done is, from each box to the gaseous atoms, I'm taking an arrow down. Round, wow, wow, wow. And this right here is your unknown, X. And now if you think about it, this is the Hess cycle. Because what do you have here? One of the three boxes is a start box, A, B versus C. Which of the three is the start box? You realize that box A is your start and the ending box is, so A to B and A to C. A to B to C or A to C. Okay. So A is the start box and B ends at C. So I can go from A to B and then from B to C. That change in multiple steps is equal to the direct change from A to C. A to B is our unknown X. B to C is 2 times 431. In this method, they're all endothermic arrows, except for whatever X comes out to be. And A to C is 436 plus 2Cl is 242. And then what do you get? Excess. So you do this, 436 plus 242 minus 862, and you would get the same answer as we got last time. So for minus 184 kilojoules per mole. Yeah. Let me show you an example. This is from your slides. This one says, using bond energies, find the delta H of this reaction. Br2 plus 3F2 makes 2 BrF3s. Now, to use bond energies, you best first figure out the structure of the molecule. So basically, Br2 is simply Br single bonded to Br. F2 is F single bonded to F 3 times. While 2BrF3, which is, this is Br, which my B is horrendous, is this. So Br, this is 2 BrF3. 3 bonds, right? Because it says BrF3. That must be this shape into 2, this structure. So basically, Hess cycle now, right? So I'm going to get my table from earlier. You remember this was my table? Hess cycle, basically. So what you do is you put the molecule in the center. So you put Br2 plus 3F2 becoming 2BrF3. This is the equation they want. This is unknown X. And box C is gaseous atoms. And you don't even have to write the gaseous atoms. Just like you don't write combustion products and you don't write elements. If you're going to use only bonds broken, then C is gaseous atoms. And what you want to do is you want to break every single thing. So you want to break the Br, you want to break the 3 Fs, and you want to break the 2 BrF3s. So this arrow is this bond breaking. That's just one Br-Br bond. Now that's, so whatever the value is, this is one Br-Br bond. Okay? And this white arrow is 3 FF bonds. So whatever the data booklet value for for FF bond is, multiplied by 3. And here each molecule has 3 BRF bonds, but you have 2 of those molecules. So this arrow would really represent 2 of each molecule's 3 BRF bonds, which is like 6 times BRF. And then all you can do is replace those values if you feel. So you will be given them from the data booklet, by the way. So for example, the yellow BR-BR is 193. They will be given to you in the data booklet. The FF single bond is 158. So it will be 3 times 158. And now the funny thing is, now this is the funny part, they don't have the value for BRF. In fact, you are asked to find this value. This is the unknown. What I didn't tell you was that this was given to us. So now you do everything like is, but you suddenly realize, hey, I don't have this value. So that is my unknown and not my delta H of the reaction. In fact, the delta H is given. Let me go back up and write it down for you. So the delta H for this reaction is actually given to us as minus 545 kilojoules per mole. So this method also not just helps us find delta H's, but using delta H and every other bond energy, you can actually find the bond energy of a particular 2 atoms. So this blue arrow in the middle is actually minus 545. And this last guy, if this is the unknown BRF, so this will be 6x, because there are 6 of these bonds, 3 in 1, and there are 2 of them. Now that you have that, now you solve it like a normal Hess cycle, because you're going to have a start box, which is A. You're going to have an end box, which is C. And you can go from start to end, which is A to B, which is minus 545. And you can go from B to C, which is 6x, equals to A to C, which is 193, and 3 times 158. All are positive except for delta H. Bond energies are positive values always. And this will give you a value for 6x. You will take this fellow that side and you will get a value here. So the bond energy comes out to, so this is X comes out to positive 202 kilojoules per mole. Yeah. I always show my bonds up somewhere so that I know what I'm breaking. So basically, the first yellow arrow, because C is gaseous atoms, okay, and I just break all the bonds. So yellow one is one HH bond, which is 436. Since it's bond breaking, everything is positive. The green arrow is breaking half a mole of OO bonds, which is half of 496. That's the unknown. And the white arrow is really breaking two OH bonds. That's 2 times 463. Start, end. So start A to B is X and B to C is 2 times 463 equals to 436 plus half of 496, because they're all positive values. And then you work out X, and that comes out to a negative value of minus 242. That's the value for X automatically. And that's the delta H of this reaction. Yeah? So basically, first of all, you got to write the equation for formation of ammonia, which is N2 gas reacting with H2 gas to make ammonia. Since it's formation of ammonia, you want to make only 1 mole of ammonia. That means you have half a mole of nitrogen and 3/2 moles of hydrogen. So the bonds broken in nitrogen are half a mole of N triple bond N. And in hydrogen, it's 3/2 of H single bond H. And you're going to make 3 NH bonds, basically. So if I write the formula here, half N2 plus 3/2 H2, okay, makes ammonia, and that is minus 46. Ammonia is NH3. And in C we have gaseous atoms. Then there's an arrow from A to C. There's an arrow from A to C again. And there's an arrow from B to C. The A to C arrow is half the nitrogen-nitrogen triple bond energy. And half the nitrogen-nitrogen triple bond energy is in the first table, which is 944. So this is half of 944. The second is 3/2 of H2, which is 436 from the data booklet. And this is 3 of the bonds you don't know. So this is 3 of each bond, which is X. And once you have the Hess cycle, then you know A is your starting box, C is your ending box. That's what it looks like from here. So starting to ending is A to B is 46 and B to C is 3X. That equals to 944/2 plus 3/2 of 436. You can even calculate that earlier, but I just didn't have that. Okay. Now this will leave to you to 3x being something and therefore x being something else. This one is 654. 944 divided by 2 is 472. All of this minus plus 46. So 472 plus 654 plus 46 is 1172 divided by 3. Gives you 390.7 kilojoules per mole.